Okay, so we are going to start covering exponential functions. We're going to be taking some notes in your packet, but before we do that, I want to just kind of talk about what an exponential function is. So just hang tight, we're not going to write any of this down. The last thing we did before exponential functions were linear functions. And what linear was repeated addition. So we might have been working a job, and that job added on $10 every week. So that was linear because every week we would be getting $10, repeated addition. Exponential is going to be kind of the same idea, except it'll be another operation that's repeated. So before I even started teaching, so I'm not even going to call this year 0, year 1. I'm going to call it year 0. Before I started teaching, when I was in college, I had 1 cat. Then, my first year teaching, I actually ended up getting 2 cats, Chester and Tuesday. Let's hypothetically say that the next year, I ended up with 4 cats. So other than a problem, what do I have? I don't have a linear function because from year 0 to year 1, I gained 1 cat, and from year 1 to year 2, I gained 2 cats. That's not linear. That's not following at a constant rate of change, right? Those are 2 different numbers. So that doesn't fall under the linear category. What I'm doing actually is I'm doubling the amount of cats I have each year. So I'm multiplying by 2. So year 3, when I multiply by 2, the 4 cats I had in year 2, I'm going to have 8 cats. So you could see how quickly exponential functions can spiral out of control. So if I were to make a table of this, with x being the years and y being the number of cats that I have, before I started teaching, I had 1. After 1 year, I had 2. After 2 years, I had 4. After 3 years, I had 8. After 4 years, I would have 16. Hopefully it doesn't get to that point. So if I were to write an equation to model this, the number of cats that I have is going to be equal to the first cat I started with times 2 each year, right? Times 2 the first year, times 2 the second year, times 2 forever. So this is repeated multiplication. That's exactly what exponential is. So the way I would write this is 1 times, the way we represent repeated multiplication is with an exponent. So 2 to the x power is going to represent however many years I teach. So by the 30th year, I will hypothetically have 10 million, no, not 10 million, 100 million. 107 million. Oh boy, nope, not 107 million. 1,073,741,824 cats. Wow, that'll be a lot of cats. Okay, so this is page 19 of your packet. We are going to fill in the notes on page 19. So let's start by writing what exponential really is. Exponential is repeated multiplication. So my equation that I came up with for all the cats that I have would be f of x equals 1 times 2 to the x. So basically we take the initial value and multiply it by whatever I'm multiplying by. So the form of these equations, every single exponential equation, is f of x equals a times b to the x. So if I match that up with my cat equation, a was how many cats I started with. So in this equation, A is the initial value. In this equation, B was how much I was multiplying by each year. I was doubling the number of cats I had each year. So we call B the growth factor if the amount is getting bigger, and then we call it the decay factor if the amount is getting smaller. An example of decay would be anytime I cut something in half. So decay is when I'm getting smaller. R isn't actually in the equation, but we can get R, which is basically the percent increase or decrease. So by what percentage are you changing the amount you have? We can get it if it's growth by taking, to get R, we take B and subtract 1. If it's decay, to find the R value, to find the rate, we take 1 and subtract B from it. That'll give us our R. So in my case, R, since I'm growing, I'm getting bigger, the number of cats is getting bigger, I take my B value and subtract 1. So my R value would be 1. But like I said, it's normally represented as a percent. So 1 is also 100%. The number of cats I was getting was increasing by 100% every year. So exponential growth happens when you have a B value greater than 1, when you're multiplying by something bigger than 1. Exponential decay, meaning the amount is getting smaller, happens if you have a B value between 0 and 1. There are no negative B values, so no negative B values. And I'll explain why in class. So if I look at the first example, this is going to be considered growth. The way that you determine if it's growth or decay is by looking at the base. So here the base is 2. Since that's a number greater than 1, it has to be growth. The initial value, how much I start with, is 3.7. So if I were to make a table of this, to start, I have 3.7. I'm doubling or multiplying by 2 every time x goes up by 1. So if I multiply by 2, I get 3.74. If I multiply it by 2 again, I get 14.8. If I multiply by 2 again, I get 29.6. And if I multiply by 2 again, I get 59.2. In this first example, if I look at it, I'm trying to see what's happening. To go from 81 to 27, I'm dividing by 3. To go from 27 to 9, I'm dividing by 3. To go from 9 to 3, I'm dividing by 3. So it does seem to have a pattern to it, but we don't define exponential using division. Exponential is repeated multiplication. So the same thing as dividing by 3 is multiplying by 1/3. So I'm multiplying by 1/3 every single time. So yes, this is exponential, and it's decay because the numbers are getting smaller. It's decay with a factor of 1/3, meaning I'm dividing by 3 each time or I'm multiplying by 1/3. And my initial value, how much I start with, is 81. That always matches up with 0. So the exponential equation here would be f of x equals my initial value, always comes first, times my, in this case, my decay factor. So my decay factor is 1/3. It's what I'm multiplying by each time. And that's raised to the x power. Real quick, if I were to find r, the rate of decrease at this function, I'd have to use this definition. To find r, I'd have to take 1 and subtract b. So this would be 2/3. My r value is 2/3, or as a percentage, I would write it as 66.6 repeating percent. Basically, you just take the decimal approximation of 2/3. Up here, by the way, my R value would have been 1 because my B value was the same as my cat function. Okay, so on page 20, I'm not exactly sure if this is exponential or not. These decimals look kind of crazy. So if I'm not sure, what I'm going to do is I'm going to divide backwards. So I'm going to do 29.04 divided by 13.2. That's going to show me what, if anything, I multiplied by to get from one to the next. So that's 2.2. If I divide backwards again, 6.388 divided by 29.04, I get 2.2 again. And if I divide backwards again, I get 2.2. So this is exponential because I'm multiplying by 2.2 every single time. And since the numbers are getting bigger, that tells me it's growth. The factor, what I'm multiplying by each time, is 2.2. The initial value I don't know. I don't see it in the table. So what I have to do is I have to divide backwards. So to get to 0, I have to go backwards by 2.2. So if I divide by 2.2, I get 6. So my initial value is 6. So my equation is f of x equals 6, how much I started with, times 2.2 to the x. And just real quick, my R value, the rate that I'm increasing by, I get by doing B minus 1. So my R value is 2.2 minus 1, which is 1.2, or 120%. Okay, so for the next one, again, I'm not sure if I'm multiplying by something each time. So I'm going to divide backwards. So I'm going to do 7.864 divided by 125.83, and that gives me 0.625. If I keep dividing, I'm going to find that 0.625 shows up every time. So that must be what I'm multiplying by. So yes, this is exponential. It's decay because it's getting smaller. My B value is 0.625. And so I need to work backwards here to find my initial value. So if I work backwards to 1, again, I'm going to divide by 0.625 to work backwards. So I get to 201.328. And then if I divide backwards one more time to get to 0, I get 322.1248. So that's my initial value. So my equation is f of x equals 322.1248 times 0.625 raised to the x power. And so for this one, my R value, since it's decay, I get by doing 1 minus b, 1 minus 0.625. So my R value in this case would be 0.375 or 37.5%. We always write our rates as percentages.